Hi everyone, Dr. Burns here with our first lesson in our acid-base equilibria chapter. In this lesson we're going to be talking about some of the basics of acids and bases, talking about how water plays into acids and bases and how to identify an acid and base. So when we're discussing acid and base reactions in this course, we're specifically referring to the transfer of a proton from one species to another in a chemical reaction. And here, when we talk about something as a proton, we're going to define that proton as a hydrogen ion. Remembering from our previous discussions that a hydrogen ion is H+, so it has no electrons. Hydrogen has one proton, one electron, as it is on the periodic table, but if we're going to make an ion out of it with a +1 charge, that means it lost its one electron. So the hydrogen ion is just one proton. So we're really just moving or transferring a proton in our chemical reaction. We see acid-base reactions every day around us. They're in our body. They're in the things we use to clean our house. We see them in nature. So if you see a sinkhole or any sort of like swimming hole type thing that's been formed in rock, that's all based off of an acid-base reaction from acidic groundwater and basic rocks like limestone. That's all acid-base reactions right there. So the type of acids and bases that we are going to be discussing specifically in this course are called Bronsted-Lowry acids and bases. Now this was brought about by Johannes Bronsted and Thomas Lowry, not that you need to know those specific names or the year in which they determined these terms, but specifically they focused on the reactions that take place between acids and bases. And what they found was there was two types of patterns in those reactions. So they were able to define a Bronsted-Lowry acid, which we sometimes just refer to as a Bronsted acid, as a compound that donates a proton to another compound. So a Bronsted acid is often referred to as a proton donor. It's giving away its proton. It has a proton, it has a hydrogen that it is able to give away to another compound in that chemical reaction. On the other hand, we have a Bronsted-Lowry base, also known as a Bronsted base, and this is a compound that accepts a proton from another compound. So the acid will donate the proton and the base will accept it. So the base is referred to as the proton acceptor. So that's why acids and bases go together so well, because the acid is donating a proton and the base is going to accept it. So anything that donates a proton is an acid, and anything that accepts a proton is a base, specifically under the Bronsted-Lowry definition of acids and bases. There are other types of acids and bases based off of definitions, which we are not going to be talking about here in this specific course. We are going to be focusing strictly on Bronsted-Lowry acids and bases where we are donating or accepting protons specifically. So let's talk about Bronsted acids first. So when a Bronsted acid donates a proton, what remains of the acid in the product side of our chemical reaction is known as the conjugate base. So here in our chemical reaction, we can see HCl is labeled as the acid. So what HCl is going to do is it's going to take this hydrogen and it's going to donate it to the base, which in this case is water. So if I'm getting rid of an H+, I'm leaving a Cl- on the other end. So what happens is in the product side, it becomes Cl-. So it's then referred to as the conjugate base. So an acid turns into a conjugate base. Here we have the base, which is the water, which is accepting that hydrogen and turning into an H3O+ or hydronium ion. So the base turns into a conjugate acid. So when we're looking to identify an acid and its conjugate base, we have to look at what that turns into. We would never say that HCl turns into H3O plus or that H2O turns into HCl. They don't match each other. So we specifically look at, well, HCl turned into Cl minus and H2O turned into H3O plus. So that's how we're going to start identifying these acids, these bases, the conjugate acids and the conjugate bases. Those two species that go together, so the HCl minus and the Cl minus, or the H2O and the H3O plus, these are often referred to as a conjugate acid-base pair or simply a conjugate pair, meaning that there has been a removal or addition of a hydrogen ion, a proton, in order to do our acid-base chemical reaction. So now for the Bronsted base, so now we're going to look at a Bronsted base instead. When it accepts a proton, the newly formed protonated species is called the conjugate acid. So the base turns into the conjugate acid. So here we have NH3 ammonia labeled as our base. And since that's the base, the water is going to act as an acid, so one of its hydrogens is going to transfer over to the NH3, leaving us with the conjugate acid of NH4 plus. I've added another hydrogen, so my NH3 becomes NH4. And my hydrogen that I added had a +1 charge, so my NH4 has a positive charge as well. The water then becomes OH minus, which is going to be the conjugate base. So why do we refer to the conjugate acid and the conjugate base in that way? Well, if our product from this reaction is NH4 and OH minus, if NH4 were to go into a reaction itself, it would then donate a proton. It has that extra hydrogen in there, it has a +1 charge, so it's more likely to donate the hydrogen, that extra proton, if it were to then be used in another reaction. The conjugate base, the OH minus, is also likely to then act as a base in another reaction where it is now going to accept a proton. We can see that it wants to accept the proton because it wants to get away from that negative charge. If I were to accept the proton, I would then have a neutral charge, which is more preferable energetically by any compound. And the same goes for the NH4+. It would rather exist without the charge, and so that's why it's more likely to now donate a proton and act more like an acid. So that's what we refer to them as. The conjugates are then the product, so conjugate referring to product, then acid base referring to would it likely accept a proton or donate a proton. So let's practice identifying compounds as either a Bronsted acid, a Bronsted base, or if they can act like both. So what we're looking for when we're looking to identify Bronsted acids and bases is we want to first look at their charge and if they have a hydrogen to give. If they're neutral and have a hydrogen to give, maybe they're going to act more like an acid. If they have a charge and would more likely prefer to add a hydrogen on there to make a neutral charge, then maybe they're going to act more like a base. So we have to look at the specific compound, look if it has a hydrogen to give away or if it has a charge that would accept a proton to see if it's going to act as an acid or a base. Our first example is water. Now, as we saw in our previous examples of acids and bases, water acted both as an acid and a base because it can create an OH minus, the hydroxide ion, and it can create the H3O plus ion as well. So water is one of the few things that can act as both an acid and a base. So it can accept and donate a proton. That's something very special about water, is it can act as both an acid and a base. Next up, we have the hydroxide ion. Now the hydroxide ion, yes, it has a hydrogen to give, but it also has a charge. So if I were to give away that hydrogen, I would create an O2 minus. And that's getting more negative, and we want to avoid that. We want to avoid getting more negative if we can add a hydrogen to avoid that. So since OH minus has that negative charge, what it's going to do is act like a base, and it is going to accept a hydrogen, a proton, and act as a base. Our next example is NO3 minus. Well, if we look, we have a charge. Yes, we have a minus charge, so it may benefit from having a hydrogen added on there. And if we look to see if there's a hydrogen to give, there's no hydrogen to give at all. So it's not like it can act like a base or like an acid, because there's no hydrogen to donate. It has to have a hydrogen to donate in order for it to act like an acid. So since there's no hydrogen, automatically it can accept a hydrogen. It's going to accept that proton. It's going to create NO3, which is nitric acid. Okay, it's going to accept that hydrogen and it's going to act as a base. So there was no hydrogen to give, so it can't donate anything and act like an acid. So the only thing it can do is act as a base. Our next example is HBr. Now this doesn't have a charge, but it does have a hydrogen to give. Now we saw with ammonia that was NH3, it acted as a base, so it had hydrogens and it still accepted a hydrogen. So when we're looking at acids and bases, we also have to think about our Lewis structures and our rules about certain elements on the periodic table, whether they want to have 1, 2, 3, or 4, or multiple bonds. Now, the structure for HBr is we have H bonded to a Br, okay, with 3 lone pairs around it. Bromine and all of our other halogens prefer to only make one bond. So it's not likely that we are going to accept a hydrogen and create H2Br. We're not going to do that because that's not preferable to our halogens. So instead, it's going to break this bond instead and create H plus and Br minus, okay, and therefore it's going to donate this hydrogen to something else, and therefore it's going to act as an acid. So we have to think about the structure of our molecule as well. If we look back to our NH3 example, so if I put it over here, nitrogen is set up like this, has 3 bonds to that hydrogen and a lone pair. Now it can accept another bond. It's not preferred for nitrogen, and it has a positive charge because of it, but because nitrogen can technically form 4 bonds, we can make that NH4+. Since bromine does not want to make any more bonds than just 1, it's going to then act as an acid more so than a base. The same can be said for our last example of HCN, which has a Lewis structure H, single bond C, triple bond N. That's our preferred structure because nitrogen would prefer to have 3 bonds in a lone pair, and carbon would prefer to have 4 bonds total, and hydrogen only having 1. Therefore, it's not like we are going to add a hydrogen anywhere. I'm not going to put a hydrogen onto this carbon because then there's too many bonds to that carbon. I'm not going to add a hydrogen onto this nitrogen because it's not preferable when it's in this setup. So what we're actually going to see is this bond is going to break, and we are going to have H plus and Cn minus, and therefore it's going to donate to hydrogen and act as an acid. For our next practice problem, we want to write the formulas of the conjugate bases for the following acids. So I have 3 acids here, and what we want to do is use those to create their conjugate base. Remembering that a conjugate base is going to have one less hydrogen than the acid, because the acid is going to donate that hydrogen to whatever is acting as the base in the reactants, and therefore the conjugate is going to have one less hydrogen than the acid originally had. So let's look at our first example. We have HNO2. Since HNO2 is an acid, it is going to take this hydrogen and it's going to donate it to whatever the base is. Okay, whatever that base is, it can be anything. So we'll just call it B for right now. So if I remove an H+, my conjugate base is then going to have the same formula minus one of those hydrogens, but it's also going to have a negative charge because I've removed a proton only, not an electron. So now I have an excess of electrons in my conjugate base. So I've removed a positive charge, so I'm going to end up with a negative charge in order to have charge balance on either side of my arrow. So our conjugate base is then NO2 minus. Now pause your video and try this for the last 2 examples here. Since the conjugate base is only going to have one less hydrogen than its original acid, only one of these hydrogens from H2SO4 is going to be removed and put onto the base. Therefore, the final formula is going to be HSO4, and it's going to have a minus charge because I lost that proton. HSO4 can act as an acid again by giving away that hydrogen. It can do it again, remove that hydrogen. Finally, we have HCN. So the only hydrogen that can give up is this hydrogen here. It's going to remove and be donated to the base. Therefore, our final formula is going to be Cn with a minus charge because I've given up just my one proton. In our last practice, we want to start identifying these acid-base conjugate pairs for each of the following reactions. So remember, as we said before, we're looking for what one reactant turned into in the product. So if we look, our first reactant is CH3COO-. Now this turned into CH3COOH. Right, it didn't turn into CN, there was no nitrogen in there to begin with, and since we're not adding or removing nitrogens when we're talking about acids and bases, it can't turn into CN-. So this accepted a proton, meaning that CH3COO- was the base, and CH3COOH is going to be the conjugate acid. It now has a hydrogen that it can give up and act like an acid if it were used in another reaction. We then have HCN that turns into CN-. This donated a hydrogen. Okay, it went from HCN to CN-, so that hydrogen here was removed. It was given to the base. Therefore, HCN is the acid, and CN- is the conjugate base. Again, CN- can now act like a base by accepting a hydrogen if it were used in another reaction after this. So as we're seeing, the acid and the base are going to be on the reactant side, and the conjugate acid and the conjugate base are going to be on the product side. So conjugate just means what it turned into in the chemical reaction. Now what I want you to do is pause your video and try these last 2 examples on your own, and then come back to check your work with me in the video. In our next example in B, we have HCO3- reacting with itself. So we have two HCO3- turning into H2CO3 and CO3-2-. So you can pick either one to start with and turn it into either reactant. So let's say this first HCO3- turns into CO3-2-. Well, what happened in that case? Well, it removed, one of those hydrogens was removed and given to the other reactant. So one of those HCO3- donated a hydrogen, therefore acting as the acid and creating the conjugate base. The other HCO3- turned into H2CO3, therefore it accepted that hydrogen, meaning that one of the HCO3s was a base and the other one was the conjugate acid. So just like water, HCO3- can act as both an acid and a base because it can both remove a hydrogen and take on a hydrogen depending on the situation. In our last example, we have H2PO4- reacting with NH3. So let's follow where everything goes. H2PO4 turns into HPO4-2-, meaning that it removed one of these hydrogens, put it onto the NH3. So it donated the hydrogen. Therefore, H2PO4 is the acid, and HPO4-2- is then the conjugate base. And then NH3 turns into NH4, so it gained a hydrogen, so it accepted a hydrogen. Therefore, NH3 is the base, and NH4+ is the conjugate acid. So let's talk a little bit more about water in regards to acid-base reactions. So in order to do this, we have to discuss ionization. So the reaction between a Bronsted acid and water is called acid ionization because water is acting as the base and the Bronsted acid is acting as the acid. Therefore, we are creating an ion in this solution. We are creating the hydronium ion. As well as the fluorine ion or fluoride ion. So it's called ionization because we are creating ions. And specifically, this is for acids because it's an acid reacting with water. Now you'll notice that if we're reacting water with an acid, the hydronium ion is then associated with that acid because it turns into the conjugate acid. So whenever we see hydronium ion, we should think acid reaction with water. So one of the products of an acid ionization is always going to be the hydronium ion. The same can be said for a base. So when a species accepts a proton from water, specifically base, so let's put basic in there, a basic species accepts a proton from water, this is called base ionization. So again, ionization because we're creating ions, except now we're creating the hydroxide ion and then an ion form of the base. I don't know exactly what that one is, but so the hydroxide ion is then associated with a base reaction. So as we're going to see throughout this chapter and throughout future chapters, if we see an OH- as a product, we had a reaction with a base. If we see an H3O+ or sometimes an H+, depending on the reaction that we're looking at, then we have reacted with an acid specifically. So in both of these examples, water was acting as both the acid and the base. We saw that in these two examples as well as the examples at the beginning of this lecture. So a species that is capable of accepting and donating protons is called amphiprotic, if we're talking specifically about Bronsted acids and bases, or it can be referred to as amphoteric when we're talking about any general species, and if it can accept or donate a proton. Those two words are kind of interchangeable with each other in general, amphiprotic and amphoteric. So we saw that water can act as both an acid and a base. We saw that HCO3 can act as both an acid and a base, which is the reactions I have here, which I'm missing some equilibria here. I'm missing my arrows in my chemical reaction. Specifically here, the hydrogen from the HCO3- is going to the water, creating CO3 2- and H3O+, meaning that water reacted with an acid. So HCO3 is then the acid, and water is the base, because we have our hydronium ion present. We can then have the HCO3- reacting with water again, where in this case, one of the hydrogens from the water is now going to the HCO3-, creating H2CO3 and getting out the hydroxide ion. So the hydroxide ion specifically is telling us that water reacted with a base. So HCO3 is then a base, and water is then the acid. So we see here that HCO3- can act as both an acid and a base. Water can act as both an acid and a base. We can also see this in other types of compounds that have multiple hydrogens on them. So we can have, let's see, some other examples would be like HPO4 2-. We could have an H2PO4-. Some versions of HSO4-, where they have hydrogens and they have a charge, so they could give the hydrogen away, or they can accept a hydrogen to neutralize that charge. We can go either way with those types of situations. This is only a small list. There are multiple examples where this can happen. Now we can take these amphiprotic species and do something called auto-ionization. So when in the liquid phase, amphiprotic species can react with themselves. When species react to create ions, this is called auto-ionization. So when they react with each other, there's no other reactant present, and they create ions of themselves, this is auto-ionization. So auto meaning that it was done automatically, it's just present because those two species are next to each other. Ionization meaning that they created an ion. So we see this more commonly with water. So liquid water will undergo auto-ionization very slightly at room temperature, with 2 out of every billion molecules becoming an ion. So if you have a water bottle next to you, you probably have a couple billion molecules of water in there. So you got a couple hydroxide and hydronium ions present in your water bottle right now, strictly because of auto-ionization, just because those 2 water molecules are next to each other and they're creating this equilibrium and acting as both an acid and a base. So you got an acid-base reaction happening right in your water bottle next to you, which is, I don't know, kind of cool. Now we can use this concept of auto-ionization to help us understand acid-base equilibria. And specifically, if we look at water, we see here, we've shown all of these reactions with equilibrium arrows in them because most acid-base reactions are in some sort of equilibrium. Therefore, if they're in an equilibrium, they can have an equilibrium constant. So K, uppercase K, is still our equilibrium constant from our previous discussions. And now they just have these different subletters. So we've talked about, Kc being the concentration-based equilibrium constant. We've talked about Kp being that of pressures. Now we're introducing Kw, Ka, and Kb. Specifically Kw, W stands for water, Ka, where A stands for acid, and Kb, where B stands for base. So if we have a reaction with just water in it, so water reacting with water, we talk about that equilibrium constant being Kw. If we have one where we're reacting an acid with water or with something else, we use Ka. And then if we're having a base that's reacting with water, then we have Kb. Now we'll talk about Kas and Kbs in a future lecture. Right now we want to focus on water. So Kw, the equilibrium expression for water, is only going to come out of the product side of this reaction. So remember that K, any K, is the concentration of the products over the concentration of the reactants. And when we're looking at equilibrium constants, we only take aqueous and gaseous products and reactants into account. So in our reaction here, where we have H2O plus H2O in equilibrium with H3O plus and OH minus, well, our reactants are both liquid water. So we wouldn't even consider them for our equilibrium expression. So the equilibrium expression only comes from the concentration of the H3O plus and the concentration of the OH minus. Therefore, Kw is equal to the concentration of the H3O plus concentration times the concentration of the OH minus ions. Now this is a K value, an equilibrium constant. It's a constant value, which we know at 25 degrees Celsius. We can find that in one of the appendices of our textbook. So we can find Kw to be 1 times 10 to the minus 14. That's the value of Kw, and this is specifically at 25 degrees Celsius. Now, Kw, as with all other equilibrium constants, will change with temperature. So the higher temperature causes more ions to form in solution. That's based off of Le Chatelier's principle and increasing the temperature. So therefore, Kw will also increase as we increase the temperature. And if we decrease the temperature, then Kw will also decrease. But if we're talking at 25 degrees Celsius, which we do a lot, Kw is going to be equal to 1 times 10 to the minus 14 for the reaction of water, the auto-ionization of water. So let's think a little bit further on that. So, because auto-ionization of water yields the same number of hydronium ions and hydroxide ions, right? It's a 1-to-1 ratio. We know that if I take 2 waters, I'm going to create 1 hydroxide and 1 hydronium. That tells us that in pure water, when I have just water in solution, so not necessarily everything in your water bottle, but let's think more theoretically that in your water bottle, all you have is pure water. We have equal concentrations of H3O plus and OH minus ions in that solution. So those concentrations are equal to each other. So if we put that into our Kw expression, we know that H3O plus and OH minus concentrations are equal to each other. Let's just set that concentration equal to X. So that gives us X times X, which can be written as X squared. If we know that X squared is equal to Kw, and we know Kw is 1 times 10 to the minus 14 at 25 degrees Celsius, well, if this is my equation that I'm dealing with, that's just basic algebra right there. I can solve for X. So I solve for X by taking the square root of 1 times 10 to the minus 14, and I get that at water, my concentration of H3O plus and OH minus ions are both equal to 1 times 10 to the minus 7 molar. And again, this is specifically at 25 degrees Celsius. But no matter what that temperature is, those ion concentrations are going to be equal to each other. So this is at any temperature. So H3O plus and OH minus are always going to be equal to each other at any temperature. So let's say we have that the ion product of water at 80 degrees Celsius is 2.4 times 10 to the minus 13. Okay? What are then the concentrations of the hydronium and the hydroxide ions in pure water at 80 degrees Celsius? So we know that at any temperature, H3O plus is equal to OH minus. We know that the concentration of H3O plus times the concentration of OH minus is always going to be equal to Kw, which in this case at 80 degrees Celsius is equal to 2.4 times 10 to the minus 13. So we can solve for those concentrations by setting each of these equal to x. So we have x times x is equal to 2.4 times 10 to the minus 13. We have x squared is equal to 2.4 times 10 to the minus 13. And therefore we can say that x is equal to the square root of 2.4 times 10 to the minus 13. So let's grab our calculators and solve this problem together. So we're going to do the square root of 2.4 times 10 to the minus 13. And we get out that x is equal to 4.89. Let's just call that 90 times 10 to the minus 7 molar, and that is then equal to both the H3O plus concentration and the OH minus concentration. So we can just continuously use this x squared is equal to Kw example. No matter what the temperature is, those hydronium and those hydroxide ion concentrations are always going to be equal to each other because of our balanced chemical equation. So as long as we know what that Kw is, we can find those ion concentrations in pure water. So let's keep practicing with that. I have two problems on the screen here, and what I want you to do is pause your video and try solving for both of these. The first one, what is the OH minus concentration in a water solution when the hydronium concentration is equal to 0.008? And an aqueous solution at 25 degrees Celsius has an OH minus concentration of 7.6 times 10 to the minus 9. We want to calculate the H3O plus concentration. So for both of these, we're now looking at, well, what if we're not in pure water? Can we still use this relationship to find our concentrations? And yes, we can. So these are not pure water solutions. We just know their individual concentrations, so we can use this relationship now to solve for the unknown. So for our first problem, if we know the H3O plus concentration and we know Kw, we can solve for the OH minus concentration. So we know that the hydronium ion concentration is 0.00800. We're going to multiply that by our factor x, and we're going to set that equal to 1.0 times 10 to the minus, too many tens there, times 10 to the minus 14. So I just have to solve for x by taking 1.0 times 10 to the minus 14 and dividing that by my H3O plus concentration, 0.00800. So we have x is equal to 1.25 times 10 to the minus 12 as our concentration. And in our last example, we're going to do the same thing, except we know OH minus, we know our hydroxide ion concentration, and we want to solve for our hydronium ion concentration. So we have X as our hydronium ion concentration, and our hydroxide is 7.6 times 10 to the minus 9 molar is equal to 1.0 times 10 to the minus 14 as Kw. So we're going to do the same thing, 1.0 times 10 to the minus 14 divided by 7.6 times 10 to the minus 9. And we get an H3O plus concentration of 1.3 times 10 to the minus 6 molar. So we can see from these three examples that not only can we use Kw, our Kw expression in pure water, where those concentrations are going to be equal to each other, we can also use that Kw expression when those concentrations are unequal to each other in non-pure water solutions. But if they're at 25 degrees Celsius, we know Kw.